So welcome back from the coffee break. When we were thinking about this conference and we were thinking about the keynotes, keynote address, whatever, we wanted to have something that would, instead of something from outside, something from inside to illustrate this ideas to impact. And one of the things that's come out of the MPP program, particularly one of the flagship projects, was the ARIOS program. And so we thought that would be a perfect kind of segue. So we actually have here two people who were involved with the program right from the beginning, okay? Candace Payne was a grad student at MIT at the beginning of the program. She's no longer a grad student at MIT. She finally graduated, right? And is now at the Aerospace Corporation doing related but work. And Helder Silva, who was involved right from the writing the proposal, is now head of aerospace flight systems at Thales, Portugal. So they're going to sort of tell the story about the ARIOS satellite and program. So up to you guys.
I did not graduate.
Did not graduate.
No, he didn't graduate. He was so.
Wonderful. I'm going to wander over here to get the clicker. Hi, everyone. Let's see. Wait for the slides to come up. Sweet. Hi, everyone. As mentioned, my name is Candace Payne. It's an honor to be here as your keynote speaker and to be chatting with you all today. I recently graduated from MIT's Department of Aeronautics and Astronautics. I defended back in December, so very recent. And am now at the Aerospace Corporation doing hyperspectral imaging work. So today, briefing you all on the ARIOS MH1 mission. So as was mentioned, it's a flagship that came out of the MIT Portugal program. And Helder and I are going to be telling you about, giving you like a general overview and then telling you about the current status and some of the lessons that we've learned. So this is what the satellite looks like. These are real images of the spacecraft before it launched. So we'll go through kind of like the science motivation to tell you like why we even care about the stuff that we're looking at, how that's related to the theme of the conference and why it's relevant to Portugal. And then I will introduce you to the actual mission, tell you about some of the technical stuff, tell you about how it works, and then Helder will give you information about where it's currently at on orbit, some of the stuff we've learned, and then we will conclude and I think go to poster session next. So just to motivate the science, I get really excited about the science, so I want you all to get really excited about the science. If you are involved in space at all, or if you are a space enthusiast, it is likely that you've probably seen this image. This is called the pale blue dot. Have you seen this before? Nods, cool. So this image was taken by the Voyager 1 spacecraft as it was on its way out of our solar system. Back in 1990, it has since left, and we are still able to talk to it, which is very exciting. But this was captured of our planet looking back at 6 billion kilometers away. And the thing that's very prominent about this image is that even from that distance, you can see that our planet is still quite blue, meaning that even from that distance, the thing that stands out the most about us is our oceans. So it kind of follows that our oceans are incredibly important to us. They're very valuable to us because they cover the majority of our planet. So I would argue that it's important that we actually care about them and learn about them as much as we possibly can. So just to kind of reiterate that point, the oceans are an incredibly valuable resource, and they're an integral subsystem of our planet. Everything that happens to the ocean affects us, whether you like it or not. As the ocean changes, we are affected by it. And here are some of the benefits that we actually have from our oceans. So as I mentioned, it covers roughly 71% of the planet's surface. The ocean is also home to millions of different types of plants and species of different animals. As I'm sure you've heard, we know very little about the creature dwellers in the oceans. There are tons of them. And as such, it actually hosts one of the most valuable species, in my opinion, which are these tiny microscopic animals that mimic plants. They're called phytoplankton. So roughly 70%, phytoplankton are actually responsible for producing roughly 70% of the oxygen that we breathe. I think trees typically get all of the credit for that, but phytoplankton are actually the heroes in this situation. And then on the economic side, in terms of actual human impact, global fisheries generate a huge number of revenue, so $200 billion in revenue, global revenue in 2022. And in that generation, they've actually supported 1.6 million jobs. And because of fisheries, they actually are a huge contributor to global food security. And in 2022 alone, they produced over 184.6 million pounds of food for people. And similar to folks that live in Portugal, folks around the world typically congregate in coastal areas. We like being near the ocean. The ocean is very fun. It's very beautiful. And so actually roughly 40% of the global population lives in a coastal region, meaning that 40% of the global population is directly impacted by how the ocean is behaving and how the ocean is changing within the context of climate change. So as I'm sure you're all aware, this is one of the themes of the conference. Climate change is actually threatening to have detrimental and irreversible effects on our oceans. Some of the things that I'm sure this group is very familiar with, but I'll just reiterate them. Some of the things that are happening are that the surface temperature is rising. If you are from the US, I don't know if you heard about the case in Florida, where the ocean water was so hot that the fish were actually being harmed. The fish were dying because they couldn't survive in the temperatures. Similarly, the water is becoming deoxygenated. That word is very challenging for me to say. Where basically the oxygen is being reduced in the water, which again affects fish health and plant health. The acid level, the acidification of the ocean is increasing, which tends to lead to things like coral bleaching, which is harmful to ecosystems that host hundreds of fish, hundreds of different thousands of types of fish. And then different anthropogenic factors like pollution runoff affect our oceans, sea level rise affect people in these coastal regions, and there are different variations in salinity density which contribute to shifting currents and tides. So because of all these nasty things that are happening, there is this need that exists for rapidly developing mechanisms that are capable of monitoring and characterizing the effects on our oceans at a global scale within the context of increased anthropogenic or human impact. So as the climate is changing, we need these solutions to quickly quantify it and understand how these things are manifesting and what that impact is actually going to look on us. And so there's a group called GSOS. So this is the Global Climate, I forgot the acronym, I'm sorry. GSOS is very important. They created this, they created this set of essential climate variables. So these are different things that we can look at that give us context about how the Earth's climate is changing. And this is a really good guide for people who are getting into wanting to have an impact on climate change, wanting to develop a system to look at something that's relevant. This list is very important. And so as you can see down here, I don't know if the pointer is going to show up. As you can see down here, the ocean is a huge chunk of this, and there's all different types of stuff that you can study. So the thing that we wanted to focus on for the AROS mission was the surface of the ocean. And particularly, we picked one of these things, right? There are so many of them, but particularly we settled on ocean color. So the question that I get the most is, why are you looking at the ocean color? Obviously, the ocean is blue. We all know that the ocean is blue. You can ask a kindergartner, right, someone who's just starting school, what the color of the ocean is, and they will tell you that it's blue. However, we actually see tons of different scales of colors that show up in the ocean. So here's a picture that was taken of the Southern Yellow Sea. So this is from NASA's Landsat 8 mission. And if you look at this image, it becomes very clear that there are all different types of things happening. So you can see different gradients of blue, different gradients of green in the image. The green is the presence of phytoplankton, as I mentioned, those tiny animals. Because you can see the phytoplankton, you can also see features in the water. So there are swirls where things are ebbing and flowing. This is indicative of how the currents in that region are moving. You can also see things like bright streaks down here. This is indicative of an ocean front, because in these regions there's something called upwelling, where cold fresh water is mixing with warm salty water. It brings nutrients to the surface and it feeds these phytoplankton. So you can clearly see very bright regions of phytoplankton just by looking at the color. Where there's phytoplankton in the water, there's fish, so that's important for us to know for fisheries. And then other things that you can see that are very directed towards humans are these little white dots across the screen, which are actually ships and boats. So just by looking at ocean color, you can also perform maritime observations locating where boats are. You can use this as indicative of where fishermen tend to congregate. And then even on the left side of the image, you can see colors like brown and tan that are indicative of things like dirt and sand and other things kind of leaking into the water. So all this to say, ocean color is very valuable. Even with one image from a satellite, you can tell a lot about what's happening on the ocean surface and in a particular region of the world. And so there is a formal definition of ocean color. This is important for folks who want to look at it from space. So that formal definition is the intensity and wavelength flux from the submarine light field exiting upwards or just from below the water surface. So the light that is striking just at the top of the ocean surface and then is being re-emitted, that is what you can actually see from space, and that is how we define ocean color. So I put a few more pictures on the slide just so you can see different types of blooms. The top is from Copernicus Sentinel-2 of the Baltic Sea. So again, you can see those swirls and eddies of the phytoplankton just by looking at its color. And down here, this is actually what's called an HAB, or a harmful algal bloom. They're also referred to as red tides, so this is the term that we typically use in the US. And this particular type of algae is harmful to humans and to fish. So when nasty things come from cities and they run down into the water, they can actually feed these phytoplankton and create these harmful things that cause neurosis in fish. So they cause brain issues with fish, which affect their behavior. And then if you're a human, it actually can cause you to have negative respiratory effects, which is not good. Yes. So just to kind of introduce what we're looking at in space, this is kind of the story. So as we know, the sun produces light. That light comes down through the atmosphere and strikes the ocean surface. So on its way down, if it makes it past the clouds, once it's in the atmosphere, it's interacting with all of the gas, all the different types of molecules that exist there. And those molecules and gas can absorb the light, which means that not all of it makes it to the surface, or they can scatter it away, which again means not all of it makes it to the surface. And then once the light is at the surface, it starts to interact with things like phytoplankton. There are other stuff that exists in the water that can either, again, scatter or absorb the light. And then once it's at the surface, if it makes it out of the surface, because water is a very nice absorber, it then has to go back through the atmosphere. If it makes it past the clouds, it has to re-interact with all of those gas and molecules, and then we can finally observe that light at the satellite. So all this to say, what you see at the satellite is not actually just the ocean surface. It includes all of these interactions in the chain. And as a matter of fact, it's actually much more complicated than this. So if you look at a coastal region, you get things like bottom reflectance. There's all kinds of stuff in the water. All types of scattering processes happen in the atmosphere. And you can get things like direct solar emission into your spacecraft, which don't actually include the ocean surface signal, or direct things from the atmosphere, which are just gases. So what you need to do is you need to understand very, very well how all these contributions are actually affecting the signal that you get at your spacecraft. And one way we do this is through radiative transfer modeling. So the thing that you want at your spacecraft is called top of atmosphere, because you're a satellite, you're looking down at the Earth, you're looking at the top of the atmosphere. And it's called spectral radiance. So this is just the light that you see from the target that you're looking at on the ground. I'm not going to go through this, but I just wanted to kind of show you the complexity of the model. And these types of models actually enable us to take all of the formerly mentioned effects into account so that we can get this giant long equation at the bottom, subtract all the stuff that we actually want, and extract this term right here, which is just the ocean surface signal. So we did a lot of this modeling before we launched EROS, which is really helpful for us to understand what the light field over Portugal would actually look like at different seasons and different types of effects that happen at the surface that I'll talk about. So now I'll introduce the mission. So this is the EROS MH1 mission. This is a fun little CAD model of the spacecraft spinning, so you can see the solar panels extended, communications antenna on top, and then some of our payloads. So I motivated the science, but EROS also has other motivations for actual development of the mission. For example, the primary objective of this mission was to develop this consortium of folks in Portugal and in the United States to have this kind of collaboration across the industry, across universities and different research institutions. And so we developed this mission to advance the Portuguese space sector, to enhance Portugal's influence and presence in space. And we did this through the development and demonstration of a miniaturized satellite. So these nanosatellites, or CubeSats, those words mean the same thing. We developed one with Portugal, and it hosted 3 different payloads. One is a hyperspectral imager, which if you don't know what that is, I will explain it. We also hosted a software-defined radio and an RGB camera for ocean monitoring. If you're not familiar with RGB cameras, yes, you are, actually. Your eyeballs are RGB cameras. Your cell phone has an RGB camera. That basically just means that you're taking 3 colors, your primaries, red, green, and blue, and combining them to make an image, and that is how we see the world. So we developed this mission to demonstrate, that we can actually throw these sensors into space and we can actually use them for monitoring the ocean. And EROS MH1 is serving as a pathfinder for future ocean observing satellites in Portugal. And the last bit here is that I'll explain a little bit on the next slide, is that through our payloads and through the operation of our payloads, we can actually serve to enhance the ocean-to-space connectivity by connecting with folks who are doing observations in situ, so in the water itself on the ground, connecting those measurements with stuff in space so that we get this full picture of what's actually happening in the area. The picture that you're seeing on the slide is the exclusive economic zone in Portugal. This is one of our primary regions of interest. Portugal has one of the largest EEZs in the world, and so it's very useful for us to monitor this area, both for like global understanding and also for to benefit Portugal here. So a brief kind of overview of some mission stats. We started the project in 2020, November 2020. I don't know if you happen to remember what was happening in the world at that point of time, but it was a little bit of a rough start. However, even though we started during the middle of a global pandemic, we were able to successfully launch this mission in 2024, so 4 years later, not even. We went from conception to launch and operation of a spacecraft, which is a very fast timeline. I think that should not be understated. If you're not familiar with CubeSats, this is again what they look like. They're very small. These are the actual size of the volume. If you're in the US, it's roughly about the size of a loaf of bread. Our loaves of bread are this big, if you're not familiar. So that is how big the spacecraft is and how powerful it is, even with that kind of small form factor. We launched to low Earth orbit, roughly 500 kilometers off the surface of the Earth, and it is very tiny. It only weighs, I think it's actually less than 5 kilos. 4.5 kilos, thank you. And so our primary payload was this hyperspectral imager that I will define for you on the next slide. And again, the other payloads, you can see them hosted here in the payload bay. The spacecraft is pointed nadir in this kind of configuration. So this camera is pointed down at the Earth as it flies overhead, which makes sense because we want to image the stuff on the Earth, not the stuff in space. And in addition to developing a whole spacecraft, the AROS team here in Portugal developed a data analysis center, which enables the distribution and dissemination of our data from space to all different types of partners. So we made this data open source and available for people. And AROS is actually the second ever CubeSat to host a hyperspectral imager that is looking at ocean color. The first was done less than a year before us, but our spectral range is actually kind of advantageous because we expand into the region that allows us to see more of those atmosphere effects so that we can correct our data a little better than the other mission. So just to introduce hyperspectral imaging, if you're not familiar, again, this is RGB imagers. You have those 3 primary colors. When you move to a multispectral imager, you get a few more colors. But for hyperspectral imagers, you can have up to 100 colors in a singular image that you're looking at, which means that you have very high spectral resolution. Because of this, you're actually able to get concurrent views of your spatial dimensions, so the stuff on the ground that you're actually looking at. And you can get all these different types of colors across your sensor in a single pixel. And this is useful because every material and every gas that exists in the universe has a unique spectral thumbprint. And if you're equipped with the right number of colors, the right set of colors, you can actually see those different material types in your image in the spectral domain. So it makes pulling out material types for the scene that you're looking at very easy. And this is useful for when you're looking at ocean color. You saw in the picture earlier how complex it is, how there's different types of phytoplankton, different colors of water, and different types of sediment in the water. So these are actually very useful for doing ocean color imaging. This is a bit more technical information. I won't go through this of the primary payload. I just wanted you all to see it. So if you were to take a slice out of it, you can see this is our optical stack here with the sensor here, and then the full stack looks like this image on the bottom left of the image panel. So the hyperspectral imager was developed by Spinworks. It is a combination of commercial off-the-shelf components. So they took a bunch of stuff. They took optics. They took a sensor. They smacked it all together and made it play nice. And it's actually a very effective way to design this imager that is high resolution, high performance, and low cost. So I would be remiss if I didn't show you some data. So this is some data. If you saw the previous slide, or if you remember the previous slide with the radiative transfer model, this is what the output of that model looks like. So we took that model, we told it to look at Portugal, we put in a bunch of stuff that told it what kind of atmosphere and aerosol types we have in the region, and it spit out that this is the signal that we would actually see over Portugal if we were looking at the coast in the summer and winter seasons. I know that this doesn't mean very much, but across the spectral space is the x-axis, and the y-axis is the actual total atmosphere, or the top of atmosphere signal. So this is the intensity of the ocean signal that we could see from space. And as you can see, it actually varies heavily seasonally. So this was important modeling work that we did before we launched to show how useful EROS would actually be for Portugal for different times of year. And these are real satellite images down at the bottom where you can see the green stuff glowing as actual phytoplankton. So you can see that in the summer and in the winter, there's actually a very dense presence of phytoplankton along the Portuguese coast, which is our target region of interest. So this is useful to know that we're not going to just be looking at stuff and see nothing. This is the same chart over here on the left. One really important thing that you need to understand is how well your sensor is actually going to be able to turn that light into an image. And you can do this by looking at the signal-to-noise ratio. So this is just telling you if you have signal coming in, if you have noise from your sensor and the same kind of concurrently, how strong is your signal actually going to be to produce this image? And so for my dissertation work, I built both these radiative transfer models. I didn't build it, but I used this radiative transfer model to model the Portuguese region, and I built a radiometric performance model to model the actual EROS imager. And basically, I fed the one with the signal into the other to show how well we would actually perform. And it turns out, even though EROS is very small, very resource constricted, we were this big, we were actually able to see pretty good signal from our hyperspectral imager. For context, the literature says that state-of-the-art imagers that are about the size of a bus or a fridge would see a signal-to-noise ratio of 200. Even though we're not able to achieve that because we don't have the same resources, we're able to see signal-to-noise ratios of 80, which is still pretty good. So the minimum in dB space is 3 dB to make sure that you have a good image. 80 corresponds to about 19, so we are well over that limit. And we skipped forward a whole bunch. This is the limit that I was referring to, this 200. And basically what we did was we showed that if we were to implement something called spectral binning, where you combine light from a bunch of adjacent bands, we were actually compliant with that requirement in different portions of the electromagnetic spectrum. And so EROS could actually perform at the same level of these imagers if we did a little bit of post-processing. But again, even without it, we are comparable, and we can still get useful scientific ocean color data from space. This is just an overview of the concept of operations. So as I mentioned, we launched in March. We then go into, we were spit out from the Falcon 9 rocket. That's the deployment initialization phase. We then go into pre-ops, where we turn everything on, make sure that it's happy. We talk to it on the ground. Our primary operations is taking hyperspectral images with our RGB imager kind of concurrently. So the visual camera that shows you what your eyeballs would see provides contextual imagery for your hyperspectral imager. Basically, if you get an image and you don't know what you're looking at, if you have context, you can actually orient yourself both in spectral and spatial domains. And then we talk to our imager with our RF communication systems on the ground. And then with extended operations, we would use our software-defined radio to then improve that ocean-to-space connectivity by chatting with things like biotagged marine life. So ocean marine life, like sharks and whales, are often tagged. And when they come to the surface, those tags emit RF beacons in the radio frequency domain. And with our spacecraft, we were actually listening for those so that we could understand where different types of marine life are congregating. And then once we saw them, we could take pictures with our hyperspectral imager to get context of how the environment looks in those regions where animals tend to be. And then we anticipate mission operations through end of life within a 6-month period. Finally, the use cases. So as I mentioned, we can see these different types of marine life. So we're able to track them and see them and then look at the environment in those areas. I also mentioned earlier how our data is useful for fisheries. So we can take images of different regions, see where there's primary productivity, direct fisheries, and fishermen to those areas. And then last, there are these things that exist called marine protected areas around the world. And our data is highly applicable to those as we're understanding the context of the environment in those regions. So with that, I will pass it over to Helder. Here you go. Thanks.
Hello, good morning. First, I would like to thank the opportunity to be here to present our satellite. And second, I would like to thank very much for the support for us to have this adventure. Okay, building a satellite, sending into space, operating it, trying to solve all the challenges is quite demanding. Okay, although we already heard several times in the media that our mission was dead, that our satellite was shy, like Rui Unas told one of the spots. is not dead and it's not shy. Okay, we took 2 weeks to find the satellite, and how is that? How we take too much? Actually, our friends from MIT told in a meeting, I do remember, that we would take 1 month. On that time, I was not humble enough and said, oh, come on, it's 2 days, I will find the satellite. No. It takes a lot of time to find a satellite. And why? Because we were launched in Transporter 10 of SpaceX in Vandenberg, in California. We are launched with 53 more satellites. Okay, so the fairing that Cadence show start to deploy the satellites. It goes, so it travels 7 kilometers per second. It starts to drop the satellites. Okay, first thing that we receive on the operations is a TLE, that is the orbit information. Say, look, you have a draft TLE. Maybe that is your satellite. We point our antennas and 0. Okay. For you to have an idea, 53 satellites at that velocity. It's all the Earth, from North Pole to the South Pole. And we have to find our satellite. It's almost find a needle. And it is worse for us because we are using a deep space antenna that we have in Santa Maria, that is the antenna number 2, SMEA2, that is very directive, okay? So we need to be very precise. If not, we fail to find it. I must say that in 2 weeks, we did not sleep very well. Okay, we knew that Portugal was on top of us, okay? But one day we found it, okay? We were pointing our antenna, we were watching the waterfall, and there it was. And after we were called by the media, and we just say, we are tired, we are going to sleep, okay? Here you can find some data that we have already tons of telemetry from space. On the right, you can say the second challenge that we had, that it was when you are launched from the exopod, that is the box that we are, the satellite is tumbling around and we have to detumbling. Okay, you can see here information from July and from August, and on August you can see that we are stopped already, and this is a very big challenge. Why? I will show you in I believe it is the next slide. Then the media again. Where is the image? We had a lot of challenge, so we have to take the image. We took already 40 images. We stop because we need to do another thing that is more urgent than taking images. And you saw in the media 3, I believe, images that we took, okay? Why? Why it's challenging? Because our electrical power system is not behaving well for 2 reasons. For the system itself and because of the next slide that I will say. You can see there a graphic with the resets of the satellite. Until today, more or less, we had 1,600 resets of the satellite. Operating a satellite with so instability is very, very hard, okay? But we did detambling, and we are trying now to sun tracking, okay? I will show you the next slide. The idea is to have a production of energy more stable and not having the resets, because it affects a lot of things, like, for example, turning on the IPEX spectral camera, okay? The IPEX spectral camera is connected directly to the batteries. It does not have a power switch. If your power system is crazy and is rebooting all the systems, we can turn on the IPEX spectral camera with the onboard computer. But if the APS turns off the onboard computer, our mission is dead, okay? So we are being very careful. With all of this, we already sent into space and execute more than 30 software images on OBC. We are being very careful, and another challenge is that we don't have engineering model in Earth to test it before we send. So the guys are coding, there is a verifier that verifies, we send to space, and okay. Okay, so we are in the troubleshooting phase, although we have everything operational with the exception of the impact spectral camera. It's quite unhappy because our friends from Spinworks are waiting for that, and we are working around the clock. So the satellite was sent into space 510 kilometers, and currently we are flying at 463 kilometers altitude. So we have still some, maybe years of operation. So we need to be careful. And this is the production last month until last week. Okay, the production of energy or the voltage of the solar panels. And what is the challenge? First, we need to equalize the top graphic. So it has a lot of sections in the satellite. You have the frontal panels, you have the lateral panels, the back panels. As you can see, it's not stable, so it's jumping. And the problem, or the challenge, I cannot say problem, is this. You see, this is 0. We never had one of the sectors producing energy for us. And it is one of the sectors of the front of the satellite. So the satellite, so it's a parallelepiped with deployed solar panels. It flies like that to the sun. This sector and this, so the one sector is the frontal panels, and these ones never produce energy. Why? I can guess, but it's just a guess. During the launch, if you go and review the launch, there are 2 lights, okay, when we will launch. It could be that we friction in the pod, okay, sad. But that's life. We have challenge. And this is what, we have tons of telemetry. The first one, it was when I start to play with it. So it's the temperature in space, okay? It is, if you do not know, it is the Sputnik mission. It was to get the temperature in space and send it to Earth. So that was our first mission. You can see it varies from minus 70 degrees to plus 45 at 510 kilometers of height. And here you can find 2 more images that we took. Eduardo already asked me, what is this? This is the impact spectral camera, okay? Things interesting about taking images in space. The first image is not any of this. The first image that we took, it was completely black. Come on. Another challenge. But the second was beautiful because we were calibrating the camera. That's why it was black. The second was beautiful. It was completely black, just a blue like this. And it was the Earth. And we made a party. Okay? So taking pictures now from space, it's not a challenge anymore. And this is the evolution that we are doing. That is one project, European project. So in Aeros MH1, we had a big challenge. That it was to make the cortex, or the radio that connects to the ground antenna to space. So we understood about how to communicate with the spacecrafts, especially the Doppler effect, because the satellite comes out, so the Doppler effect is very good. And this is our improvements, okay? We bought the satellite part on board, but we already know how to improve it in terms of power consumption, because it consumes around 12-14 watts. It's too much. We believe that we can reduce to half, or less than half. And another thing, that when the satellite starts to be in the visibility, we have to sweep the frequencies to compensate Doppler and to lock the satellite. And we have already a mean not to do that. It's not a problem when it appears and we sweep and we connect, we lock, and we have a good passage, okay? The problem is when in the middle of the passage you lose the lock, so you have to sweep again, and okay, so we improved a lot, and we are doing this in an European project for air combat, okay, and in the work package 7, that is the communications, okay? And what we have been doing. So I can say that although I'm not a graduate, I'm an aerospace engineer, and I'm in aerospace because once, when I was in 11th grade, someone went to my classroom and spoke about aerospace. So I'm doing the same now. Okay, this is a lecture that I provide to some young people. They are very enthusiastic. I've been doing that since the launch. They are very enthusiastic. They ask a lot of tough questions. What was the price? Okay. And one thing that it was really nice when I was ending the presentation, they made a queue with the paper and a pencil. Please sign. Okay, it was really good. You can see also other initiatives that we are involved, were involved. That is, it was CANSAT in Santa Maria for high school people to build a CANSAT, and it is missing another one that is the CubeSat initiative from Portugal Space, that we are mentoring 2 teams from universities, and we will have a workshop with all the teams just to discuss how to build a CubeSat. Lessons learned. 9 months for integration of assembly, integration and test a satellite, it's not enough, okay? And why? Because we had COVID, as Kaden said, it was tough, but even tougher than COVID, we were meeting in Zoom, in Teams. It was the chip shortage in the end of the phase. We did not have parts for the satellite. We wait, and it appeared in the end, okay? That was very tough. Another thing is the documentation from New Space. It has a lot of issues, and some of them we just found in space. Like, for example, the documentation of the radio, it was not correct, for example, for the Doppler. Okay, we had to find it out in space. And another thing that I already told, it was regarding the engineering model. So production in space is very hard. We need to have an engineering model in space to try before we send the software to space. In terms of the payloads, we believe the next missions would need a broader imager that would allow us to go down in the bandwidth and go up, especially going up, if I'm correct, because with infrareds, we can know the temperature of the am I speaking correct? Okay. And also to have a uniform spacing of all the bands in the imager. It's you, Cadence.
Cool. Yeah, no. What Hunter was mentioning, if we, there we go. Yeah, what Helder was mentioning was that if we extend our spectral response of the hyperspectral imager, we can get deeper into blue bands, which would help us be more applicable for different types of algorithms, and then extend farther into the SWIR, the shortwave infrared and near infrared bands, so we get more information about the atmosphere. And basically, like, the more context that you can get for your ocean surface image, the better. So now we know that even with Eros, we have the possibility to get really good data, but we could improve upon it. But yeah, thanks, Helder. That was great. This is a video of them integrating the satellite into the exopod dispenser. So basically, when you stick yourself in a rocket, you can't just slot into the rocket. You have to slot into another box first. So this is what that box looks like as people were doing this kind of fit check prior to delivering to the launch vehicle provider, which was SpaceX. Yeah, so just to wrap up, overall, Eros MH1 has been a successful demonstration. We've demonstrated Portugal's capabilities to design, develop, launch, and operate nanosatellite platforms. Eros was Portugal's very first nanosatellite mission, which is a huge endeavor and I think a huge accomplishment, even with all of the aforementioned issues and problems. Unfortunately, like CubeSats, the rule of thumb is that they are inevitably going to hurt your feelings. They tend to break. Things tend to go wrong when you get into space, especially with all of the chip shortages and the shortened timelines. I think we should still be very proud of the fact that we were able to launch the satellite and get images down, and we have the bandwidth to still operate it. So I think it's been a huge success. It is serving as a pathfinder for future missions in Portugal, as Helder mentioned one of them. Is currently underway, and now we know all these lessons of how to improve upon the next design to make the next mission even more successful. And as I mentioned earlier, EROS is only one of 2 of these satellites doing ocean color imaging with hyperspectral cameras, which is incredibly novel for the nanosatellite community. I don't know if you're familiar with NASA PACE that just launched, but prior to PACE launch, there wasn't any hyperspectral imagers looking at the ocean on orbit at all. So I think that is also a huge accomplishment, and that we're pushing into the nanosatellite space domain and showing that with this thing developed by Portugal, we can actually take really good measurements. We have the potential to take very good measurements. And the SDR, right? The software-defined radio. Yeah. So all this to say, the integration and the support of the MIT Portugal program was absolutely critical for the development of this mission. I'll hone in on that in the next slide. But MIT, this program gave me the opportunity to engage with Portugal and to participate in this mission from conception. I received the proposal on my desk when I was trying to figure out what I wanted to do with my PhD, and I got to stay with the team through launch. So that was unprecedented. Not many people get the opportunity to see a mission from start to finish in their graduate career, and I was able to do that through the MIT Portugal program. And because of all of our success, I want to highlight the fact that EROS was actually awarded AIAA's Nanosatellite Mission of the Year, which is a very competitive, very prestigious award. We beat out other small companies that were launching stuff with entire companies of people, and we did it, with our team and with all the aforementioned issues. So I think that is something that we should be very proud of. I want to, I'd be remiss if I didn't get on the stage and tell you all how applicable we are to climate change. The UN Sustainable Development Goals, I'm sure you've seen these before. We are directly applicable to goal number 13 and 14 for climate action and understanding life below the water. We're attempting to monitor things on the surface, but with our software-defined radio, we can also, again, bridge that connectivity to things that exist in the water and understand the impact on their environment. And again, this is kind of relating back to the Global Climate Observing System, there's the acronym, in terms of their essential ocean variables that they developed, and showing how we can actually support the monitoring of those things that we know are useful to understanding the climate. Project contributions. Over the course of this work so far, we've had 11 publications and presentations. We've had 4 different conference publications, all which are accompanied by papers that you can go look up and read if you want. We have submitted 3 posters to this conference, one of which won Best Poster Overall. And we actually have a journal publication and process with AIAA's Journal for Spacecraft and Rockets. It's currently being reviewed. Hopefully we get nice things back. I think it's a very good paper, so we'll see what the reviewers think. And then EROS was actually a primary case study in my dissertation. It was basically, the work that I did was half of the work that I did for my PhD, so I can't thank you enough for allowing me to work with you to do something that I think is very useful and very impactful. It felt really good to be able to do my PhD on a topic like this. So with that, here's some more pictures. These are other first light images that I think I will leave up as we go into questions. But just to highlight, the efforts for this project were huge. They spanned across all different types of companies in Portugal and MIT in the United States. Particularly only at MIT, it was with my lab, the Space Telecommunications Astronomy and Radiation Lab. But all of these different groups of people came together to finance, develop, and support this mission, again, from conception through launch. So I would like to extend a huge congratulations to all these people and a huge thanks for allowing me to be a part of it. I inherently think that if we move forward in the space domain, particularly in terms of developing and launching things that are relevant for understanding climate change and mitigating climate disasters, we are required to have international collaboration because space is an international domain. Nobody owns it, and we need to play nice with each other in order to continue to solve these disastrous, monstrous problems that are kind of plaguing the world. And I think MIT Portugal program is well suited to make sure that that collaboration kind of stays put. So with that, I would like to thank you all, and we have a couple of minutes for questions, I think. So.
Yeah. Any questions?
Not difficult ones.
Easy, easy.
Oh, I was going to ask you what the meaning of life was or something.
Okay.
Yeah, what's the price? First of all, there's orders of magnitude more difficult to put real hardware into and to get it to work than it is to do paper studies. So my hat's off. I'm incredibly impressed by the outcome from this. But I have to say, you know, from the MIT Portugal side, the real success is, although this is impressive, the real success is you guys and the collaboration that has been established. So to me, that's the highlight for me of this.
It's been hard, but we've had a lot of fun. So.
We tried to be a team.
I think you succeeded.
And it's not only us. There are several.
Yeah, several people of our team is. Yeah.
Yeah, raise your hand or stand up if you were
please.
part of.
Can you?
Woo!
I have a question. You chose a harder problem than most. I come a little bit from the agriculture side, where they do spectral imaging for plants and stuff. And there, they have a much easier task in some sense, because the way they do the radiation modeling is to put targets out on the ground near the plants themselves in the field, and they can get very accurate reflections models back, so they know what they're doing. You've got a much more difficult problem of trying to handle this. How do you go about that? You can't. Could you put a radiation reflector out on the ocean on the surface or something? I mean, how do you? And how bad is this? Is the errors in the model affect your data?
I guess we don't have data from space yet to answer that last question, but the question of how do you perform vicarious calibration from orbit to make sure that the data that you're getting with your imager is accurate is a hard one, especially when you are looking at potentially open ocean, when you don't have any kind of land references to know where you're pointing. So how do you actually know what you're looking at? There are different types of very well-characterized features, and there are databases of regions of the world, especially like over coastal or open ocean areas, that are very well-characterized and monitored daily, sometimes with in-situ buoys, that tell you the ground truth of the area that you're looking at in terms of the actual upwelling surface flux coming out of the water. So that is one option for us, is to look at that data that exists, to be like, okay, we're imaging this portion of the world, we know what it's supposed to look like, how do we compare? So that's one of our plans. With hyperspectral, we're in the visible and near-infrared region. So we could, there are places that exist in the world that have these targets that are already very well characterized already. So we, I think, have some coverage of ground truthing there. And then the last option is that for imagers that exist like MODIS or VIIRS on board NASA's Aqua and Terra, they take daily imagery of, I think, most of the world. And they are very well characterized, they're very reliable, and so that's another option, is to compare our actual reflectance measurements with their data as an additional kind of co-boresight ground truth.
Are there other questions before we?
That was a hard question.
Yeah, well, it's Doug. All right.
You said an easy question. Okay.
All right. Yeah.
I can answer.
Yeah. Okay, well, thank you guys, and this is really great project. So we're gonna now move to the poster session, and you all saw them when you came in. The posters are out sort of on the entrance. So thank you, both of you guys.
Yeah, thanks.